Replicated structures. So replicated structures, as it turns out, that a lot of digital systems have a very systematic patterns that is of replicated structures. And again, we're describing hardware. So whatever we do, and we want to do something over and over again, all we have to do is use a for loop. We're not doing it sequentially, but we're going to replicate it. So replicated structure, you can see structures similar to this, or a full adder, for example, you've seen it, or a bunch of full adders in here. You can see this is a binary adder because it's going to have, this is a 1-bit adder, this is a 1-bit adder, this is a 1-bit adder with a carry in and carry out. If you actually cascade it this way, you get this one here is a 4-bit adder, okay? And frankly speaking, what I'm trying to tell you in here is, okay, you might build the full adder circuit here, and what happens is it doesn't make sense that you're going to write code to instantiate version here and another one here, another one here, another one here. What if I have 100-bit? Are you going to instantiate 100 versions of it? It doesn't make sense. So there might be a better way, and that better way is actually for loops. Okay, there's a couple of these for loops. There's something what we call a concurrent for loop. Okay, a concurrent, similar to the continuous assignment, lives outside the always statement. It's not part of the always statement. And this particular code in here, just you're gonna see it's not the best way to implement an XOR. This is an 8-bit input XOR. Okay, but what I did is I basically implemented it in the cascading XORs, a bunch of them. So you create an XOR of two. Well, you don't have to create an XOR because it already exists as an operator. Okay, and you do basically the same. I think I have a typo in here. This should be an operator like this. It's not a negative. It's actually the operator, the XOR operator. You already have it. So you can take a look at this. You will be using it in one of the labs. This is what we call a reduce XOR. Frankly speaking, you don't even need this. Like you can actually put the A and you can say XOR A. This is a reduction operator. Okay. But for the sake of argument, I just want you to see something that is very structural. You can see it here. There's no always statement in this code. What we have is we have this particular one, which is generate and end generate. What you're doing is you're generating a bunch of XORs, and the way we do it is you have a generate var similar to the integer I. It's basically just an index, and you have a for loop. This is a for loop similar to what you do in C. It's not acting like C, but its syntax and the way you can think about it is like C. But what it's doing is actually creating these circuits in here. So if you are actually iterating over 100, you're actually using 100 circuit elements, which is not always feasible or correct. Okay, so read this code and you can see it's pretty simple to actually understand. It's not very bad, and you can see how you're doing it. This is what we call a concurrent for loop. Okay, this lives outside an always statement. It's within a generate, and I have used it multiple times. Sometimes I have like a more complicated structure and I want to basically just connect it one to the other or sequentially, one after the other, and I just use the generate or gen var. Okay, I usually think about it generate gen var I. That's how I remember it. Okay, another type of for loop, it's actually a procedural for loop. It's pretty similar, but this one actually lives within an always statement. So generally speaking, the procedural, the concurrent one is you're actually describing complete hardware. There's no behavior here. You're just connecting hardware to each other. You're just replicating hardware specifically and explicitly. Okay, when you're doing with procedural for loop, you can do what I did before, but frankly speaking, what you're doing here is you're describing the behavior of the circuit that you choose to. You're going to see that both codes are extremely similar because this example is pretty simplistic, but you get the idea. So you have a procedure for loop. Probably you have seen this and you have used it multiple times. Please make sure do not write code that actually iterate over 1,000 times or a bunch of for loops inside each other unless absolutely necessary. I don't usually see it necessary when you have a for inside another for. Unless like you probably are generating something like a grid, like the grid we saw, chances are you don't want to do that. Okay, and this is basically about the procedure or the for loops or replicated structures. Okay, so this is for the sake of completion. This is how we implement this particular multiplexer using the for loop. I just kept it. You can read it and figure it out. So you have another example. I have a for and I have an if nested in each other.